Calculus students, and especially general seekers of truth. In the last video, we worked on some area functions, and hopefully you got a sense of what it is that an area function really is. Now we're going to talk about some more conceptual things. So let's go back to this function f of x. If you notice, when you plug in x, when you plug in 1 for x, you get 1 for f. 2 for x, you get 4 for f of x, 3 for x, 9 for f of x, 4 for x, 16, and so on. So this suggests that f of x is going to equal x squared. Okay, so this is important. F of x is equal to x squared. Okay. Now, let's look down here at g of x. This is a little bit harder to see, but you can notice here that these values are increasing from -8 to -5. It increases by 3, and then by 5, and then by 7, and then by 9. So g of x is also a function related to x squared. It's x squared, but minus 9. Okay. So if you just compare the values that you have for g and the values that you have for f, you'll see that, and maybe I'll write it along here. If you compare the value for f of x, we had 1, we had 4, we had 9, 16, and 25. Well, it's not really by any coincidence that you see that the values for g are exactly 9 units smaller than each of the values for x. So g of x is equal to x squared minus 9. Now, what does this really have to do with anything? Well, let's look at a few things. F of x and g of x look very similar. They are, what do they have in common? Well, they are integrals, or they're definite integrals under the curve of y equals 2x or 2t. All right, so they both have that. And one more thing that, you know, in calculus terms, f prime of x is equal to 2x, and g prime of x is also equal to 2x. And maybe one other thing we can notice is that the derivatives of f and the derivatives of g also match the actual curve itself. Okay. So this is a relevant and an important point. And, you know, it's really by no coincidence that the derivative of these area functions happen to equal the function of the curves. Okay? Let me say that again. The derivatives of the area function is equal to the functions of the curve. All right? So this brings me to the FTC, and I should say that the FTC stands for the Fundamental Theorem of Calculus. Okay, the FTC. Part 1. Now, textbooks don't really agree on what's part 1 and what's part 2, but they do agree that there's 2 different parts, and I'm going to call this the antiderivative part. And it says as follows. Given a function f, little f of t that is continuous, and a area function, we'll call this big G of t, and that's equal to some constant to x of f of t dt. Okay, so just to be clear, k is a constant. It could be 0, it could be 1, it could be whatever. Then the derivative of g is exactly equal to x. In other words, the derivative of the area function is equal to the function of the curve. Another way we can say this is that g of x is the antiderivative of f of x, or f of t. Okay. And this says something quite powerful, that somehow this concept of antiderivative and this concept of definite integral are actually related. And not only are they related, they're exactly the same thing. So finding the antiderivative and finding area is related to each other. And it's basically the same thing. Right? This is not intuitive. This is not a definition. This took a lot of energy in order to prove. We are not going to prove this in this video or in this lesson, but we are going to use it. All right. So this is the fundamental theorem of calculus part 1. And it says, once again, that if you have a function that's continuous, then it has an antiderivative. And not only does it have an antiderivative, that antiderivative is equal to the area function. So I will end this here, and then I will show you a bunch of examples in the following video.